Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Raise your hand if you did not get a red mark for today, the 2nd of December. Okay, let's get going. And so last activity, we investigated linearization, a concept which uses tangent lines to approximate function values. And then we used tangent lines not only to develop an approximation for function values, we also introduced the idea of differentials, which we're going to need today as we go backwards and evaluate indefinite integrals. And so we'll talk about the difference between a differential, which just is a single term dy there, as opposed to the term we're familiar with, dy dx, right? Y prime, the first derivative of y with respect to x, and we'll talk about those differences a little bit later today. And then we're going to go ahead and evaluate indefinite integrals, which is the same as finding antiderivatives. So you need to know your derivative rules. You need to have them memorized. You need to know them forward and backwards. Now we have to be on the lookout for a derivatives rules quiz, which could show up anytime, right? We need to know our rules by heart and by memory. And so not today, but we could have a rules quiz next class or the class after or the class after that. We have to be good with our derivative rules in order to be good with anti-differentiation. Okay, so let's go ahead and get going with our Bellwork today. The linearization of f of x is simply a tangent line to the curve at a particular x value. And we know all about that. We just have new packaging. So now instead of calling it y equals, we'll call it L of x equals for our linearization. It's a line whose slope is given by f prime. F prime is the first derivative of x, but we're going to evaluate that at the x value of concern. So f prime of c would be my slope of the tangent line. And then again, my x minus x sub 1, the particular x sub 1 value is c, so x minus c. And then we'll add over that y sub 1, so plus f of c. And that was our first stamp from our activity 5.2. Well, go ahead and raise your hand if you had that for L of x. That's our generalized form for L of x. That's just a tangent line. It's my y minus y sub 1 equals m times quantity x minus x sub 1 in disguise in new packaging. All right, the differential dy now can be interpreted as a small change in y predicted by the tangent line as we move away from our point of tangency. And so dy is given by f prime of x dx, where f prime of x is the derivative, the first derivative of my function f with respect to x, and dx is this very small step that we're moving over. It's equivalent to delta x, right? Dy is different, however, than delta y. Delta y represents the exact change in function values as you scoot over delta x units, versus dy is my predicted change in y values using the tangent line or my linearization. So there's a distinct connection between dy and delta y and L of x, right? Dy is my predicted change in the y values, right, based on my linearization. So this is a very small change in y based on a very small change in x. All right, so let's go ahead and do it in context of a given function, f of x equals x cubed. Then dy equals f prime of x dx. If f is x cubed, then f prime of x is power roll 3x squared, and dy would be 3x squared dx. This looks familiar, right? This looks familiar. This dy differential equals 3x squared dx. That comes from, in a sense, our Leibniz notation, which we're already familiar with. If y equals x cubed, then dy dx, the derivative of y with respect to x, equals 3x squared. And you can see how we would get to this blue answer, dy equals 3x squared dx, if we could, just separate this dy dx. Instead of thinking that as a single term, y prime, right? If we could just separate the dy and the dx and multiply this dx over the other side, we'd be left with exactly dy, okay? And that's what differentials do. That's also going to enable us to go backwards and find antiderivatives today in class. So that's super important. And I did make a slide that we'll discuss in just a little bit. All right, at x equals 3, L of x equals, well, that's just my equation, my tangent line solved for y. So remember, we can start with my y minus y sub 1 is equal to m times quantity x minus x sub 1. In this particular case, we'll call my equation of the tangent line y equals, we'll call it L of x equals. And so we've got my f prime evaluated at x equals 3. F prime is 3x squared. We'll evaluate that at x equals 3, so I'm getting 3 squared is 9 times 3 is 27, so I'm getting 27. there's my slope of the tangent line, times quantity x minus x value of concern is x equals 3. Closed quantity, and then I'm going to add over that y sub 1, right? The value of the function at x equals 3, and that is 3 cubed is 27. And so that's 27 also, but a very different 27. This 27 is the slope of the tangent line. This 27 is the value of the function when x equals 3, right? So this is the 27 from the point of tangent. Awesome. What questions do you guys have about number 3? All right, then to be good at evaluating indefinite integrals, which is just finding antiderivatives, we have to know our derivative rules. So everybody go ahead and think of your classroom number. I'm going to call on you to share your derivative rules. If you want to take a look at your rule sheet and have that hiding by your binder, that's totally fine too. I want you to be ready to recite this, and I'm going to use the random number generator to call on you. So go ahead, get set. Get your classroom number ready. 29 or 28? 29 or 28? We'll go 29. We'll go for it. All right, get set, get ready. You're going to share with the class, and you're going to complete the derivative rules in words, right, when your number is selected. So get ready. The derivative of a power function is number 20.
In words?
Yeah, in words,
Okay, sorry. Okay.
You can use your rules words sheet,
Yeah,
right?
Is it the exponent times the base raised to the 1 less?
Yep, and then in accordance with the chain rule, times
Derivative of the x?
the derivative of the base, right? The inner function in accordance with the chain rule. So the derivative of a power function is the exponent times the base raised to 1 less, and then times the derivative of the base. That includes the chain rule, right, in words. Get ready. The derivative of a product of two functions is number 22.
The derivative of the first times the second plus the first times the derivative of the second.
Absolutely, good. Thank you. The derivative of a quotient of two functions is number 27.
U prime times b minus u times b prime over b squared.
So long as u is the
Numerator.
of a quotient and
B is the denominator.
good. And so the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Good. Thank you. Get ready. The derivative of a trig function is number 1. Let's see. Number 1? Yeah.
I'm not sure.
You can get your rule sheet, right, in words. The one in words when we were out, yeah. In fact, why doesn't everybody just get your rule sheet ready so that we're ready to go when I call on you, because I'm going to call on you with your random number generator. I'm going to call on you. So get ready, get your rule sheet. Maybe that, oh, that goes sooner rather than later. Absolutely, and remember our trig function words was the easiest way to see the chain rule apply. It's the derivative of the overall trig function with the angle, with the inner function, and then times the derivative of the angle, times the derivative of the inner function. So this is a perfect application for the chain rule in a specific context. Good, thank you. Get ready. The derivative of an exponential function is number 15.
Natural log of the base times the exponent times the derivative of the exponent.
Careful, times the exponential itself, then times the derivative of the exponent. And so remember, the exponential itself, right, shows up in the derivative, and that's why exponential functions with base e are typically used in calculus along with natural logs, their inverse, because their derivatives and integrals are so easy. They're cyclical, right? Good, thank you. The derivative of the inverse sine is, oh, we have to know this one? Yep, gotta know this one. Number 17. Absolutely, good. Thank you for including the chain. The derivative of the inverse cosine function is number 24.
That's easy.
Thank you. Number 7.
-1 divided by the square root of 1 minus the input squared times the derivative.
Thank you for including the chain. The derivative of the inverse tangent, one of my favorite rules, number 25.
1/1 plus the input squared times the derivative of the input.
Solid, thank you. The derivative of the natural log of a function. The derivative of the natural log of a function is number 10.
1 over the function times the derivative of the function.
Perfect, thank you. And last but certainly not least, the derivative of a constant is, who gets it? Lucky number 26. 0 is correct. So the derivative of a constant is 0. So we have to know our words, right? We have to know our words, and we have to have them memorized, because today we're going to begin finding antiderivatives. That is, going backwards. You're going to do a little bit with your partners, but we're going to do some whole group discussion as well. And we're going to look at two different techniques. We're going to informally find an antiderivative, and then we're also going to look at a technique called u-substitution, which will allow us to systematically determine any missing constant multipliers that might be necessary for my antidifferentiation. Very well. All right. But first, let's go ahead and get you guys credit for your OTL number 4. So at this time, if you kindly take out your OTL number 4, you don't need to staple the half sheet because there was not a graph on the back of that, so we just need your bookwork. But if you do have multiple pages, I kindly ask that you staple those together so that we don't lose those loose papers, and you get credit for the hard work you're doing outside of class. Make sure that your name, first and last, 1B, number 4, are clearly labeled. Give yourself credit for those who complete out of 18, please. Enter, let's box that infinite canvas score nice and big. Make sure you guys are giving yourself an infinite canvas score on top. Box that nice and big down to the nearest half point, 0 to 2, and then pass from the back to the front, please. Front rowers, make sure they're facing the same direction. I appreciate your help. Everybody good? Number 4? Awesome. Okay, and so we need differentials so that we can find antiderivatives. So we need differentials so we can find antiderivatives. How come? Well, let's go ahead and consider two different notations. That's Leibniz notation, which dy dx, right? We used that when we were doing our implicit differentiation, when we were doing our related rates, right? We had our dv dt, or our dA dt, or our dy dt. Leibniz notation is dy dx, that would be the derivative of y with respect to x. That's synonymous with y prime, or dy dx equals f prime of x, the first derivative of f with respect to x. What differentials does is, instead of thinking of that dy dx as a single factor, a single quantity, the instantaneous rate of change in y with respect to x, what linearization does is it breaks up the dy and the dx as two separate quantities. And so it breaks them up as two separate quantities. It allows us to separate this, kind of multiply over that dx to the right-hand side, and generates an expression dy equals f prime of x dx. Okay, dy equals f prime of x dx, where this dy can be interpreted as a quantity in its own right, a small step in y. The predicted change in the y value is based on my instantaneous rate of change of the function at a particular x value. That's my f prime of x evaluated at a c value if we needed to, and then times dx, which is a small step over, right? It's just a small step over. That's like if you're driving at a rate of 60 miles per hour, right, on the highway, and you travel for 5 seconds, what's our predicted change in my position y? Right? That's exactly what this linearization does for us. It enables us to predict a change in y. Thank you. Oh, she's not here today. To predict a change in y using a tangent line, a linearization. Okay? So suppose y equals x cubed. Well, we saw this one. We know then that my dy dx would equal 3x squared if we were now to break up, this dy and this dx, and interpret them as separate quantities, we could multiply this dx over to the right-hand side, and then dy, the small change in y, predicted change in y based on my tangent line, would be given by 3x squared times dx. And so we'll need that notation later. Awesome. Okay, so for our warm-up today, we're going to go ahead and find y prime if y equals sine of 3x minus 7. Be ready to share with the class because I'm going to call on you, and I may or may not use the random number generator, just in case some of you are nodding off back there. I see you. So let's go ahead and write y prime for each of these. If y is sine of 3x minus 7, then what's y prime? If y is 5 plus sine of 3x, then what's y prime? If y is sine of 3x plus 8.57, what's y prime? Okay, enough talk. Now we eat. So if y is sine of 3x minus 7, what would y prime be given by? Andrew?
3 cosine of 3x.
Sine of 3x. Awesome, thank you. If y is 5 plus sine 3x, what would y prime be given by? Vivian?
Negative 3 cosine dx.
So if sine differentiates to cosine straight up, so positive 3 cosine 3x still. Thank you. And if y is sine of 3x plus 8.57, then y prime is given by Danny?
3 cosine 3.
So if y prime is 3 cosine 3x, then what's my original y? All right, what's my original y? Tyler?
Sine of 3x plus anything.
Yeah, sine of 3x, right, is my parent function that differentiates to the 3 cosine 3x, but we could have had some constant like 8.57 or 5 or negative 7 or pi attached to the end of my original y that we wouldn't know about, right? When we differentiate, the derivative of any constant is 0, and so we have to account for that unknown constant by including a plus c when we go backwards. That is, when we find an antiderivative and step up from y prime to an original function y, we need to include a constant of integration, a plus c. This constant of integration here accounts for the fact that any constant could have been added or subtracted onto my original parent function y, and we wouldn't know what it is when we differentiated it to get our y prime. So we're going to include that in all of our anti-differentiation and our evaluations of indefinite integrals, which just means to find an antiderivative. So we must include a plus c. So on your note sheet, indefinite integrals, this topic for today, we're going to be evaluating indefinite integrals, are just antiderivatives. G is an antiderivative of f if and only if the derivative of g is f. In this way, differentiation and antidifferentiation are inverse processes. So g is an antiderivative of f. That's what that notation on the left means. If and only if the derivative of g is f. Because indefinite integrals are antiderivatives, we could also restate this as g is an indefinite integral of f if and only if the derivative of g is f. So antiderivatives and indefinite integrals are synonymous. Michael.
Why do you have, like, since they're basically the same, why do you have them both?
They are the same, right? They're the same. You mean the left and the right hand side? Just to provide a definition. So we're seeing that g is an antiderivative for f, right? If and only if the derivative of g is f. They are the same thing, and we need that, right? Because we're providing a definition. That's what it means to be an antiderivative. If you differentiate it, you get back to the original, okay? While we're here, though, it's important to note that this quantity f of x here inside my indefinite integral, this is called the integrator. It's called the integrand. This elongated S is called an integral symbol. And if there are no limits, that is no numbers on my integral symbol, then I know I'm evaluating an indefinite integral, which means find an antiderivative, a function, right? A function that includes this variable in it. And so this is telling me my independent variable. This is dx, this means with respect to x. So the independent variable in my function is x. When I go and find the antiderivative function, I'll have x's in it. When I differentiate that antiderivative function to get back to my original integrand and checked it, I'll have x's in it. Right. So that's for printing, and that's for you. And don't forget the plus C. You're going to have your first opportunity right now with your partner to see if you can't find original y from which they came on my differential equations review. Pay attention to detail. That is, if it's dy dm, then my independent variable must have m's in it, right? My original function must have m's in it. If it's dy dt, then my original function y must have t's in it, okay? Right now with your partner, let's go ahead and complete differential review. I'm going to ask you to come up and write your responses here on the smartboard, so please don't be anxious to be asked to do that. You're welcome to bring your paper up with you. And so let's go ahead and get started right now. If you don't have a partner, you can scoot to someone who does have a partner, and I'll be asking you to come up and share your responses on the whiteboard. Thank you.
It was done to that equals down 1. So 36. There's times 5, which means 36. X.
Yeah, that's okay. And I did stand. You can just take it. Okay, thank you.
Oh, this thing, okay.
And then you go right to special on the board and see greater than 3 for fraction include.
You guys should all be on the differential equations review. One-page, single-sided, and match on the smartboard. And I'll be asking you to come up and share your responses on the whiteboard. Thank you.
Cosecant. Yeah, cosecant cotangent is the derivative of cotangent, right? Cotangent is opposite cosecant squared. Cotangent goes to opposite.
Oh, negative. Yeah, negative cosecant. I saw your negative. No, I said good job with the sign. Yeah, negative.
Cosecant. Negative cosecant. No, it's negative cosecant.
Yeah, no, I see that.
Yeah. So it's just negative cosecant.
get it because cosecant goes into negative cosine. So it's a negative. So the opposite, so the negative will go away and the cosecant comes into cosecant.
No, but you did the X.
This is just one view.
Okay, ladies and gentlemen, let's come together. Some of you are still finishing up, and that's fine, but I do want to check the antiderivatives that those of you supplied as you came up to the whiteboard. So thank you for those of you who came up and shared your responses. I appreciate that. Let's everybody take a look. So for your differential equations review to be completed with partners, an antiderivative for 36x to the fourth is 36 x to the fifth plus c. Where did this divided by 5 come from? Well, we know that my power rule does exponent times the base raised to 1 less. And so if I'm going backwards, I'm going to have to increase my x1 by 1. We went from x to the fourth to x to the fifth. But then I'm going to have to divide by that new exponent. How come? Because division undoes the multiplication if I were differentiating, right? Exponent times the base raised to 1 less. I'd have to undo those operations in reverse order, so I'd have to add 1 to the exponent and divide by the new exponent. And that's how we get our 36 fifths x to the fifth plus c. And we can always check by differentiating. 36 fifths times 5 x to the fourth. The 5 over 5 cancels, and we're left with the original 36x to the fourth. Nice job. Raise your hand if you had one correct. One correct. Good job with assignment number 2. This is negative cosecant of x plus c. Raise your hand if you had an antiderivative that matched number 2. Good job. dy dm equals -7. Then my independent variable in my original y function must have been m. Nice job with that. -7m plus c. Raise your hand if you had that. -7m plus c. Good job. The fourth one, term by term. If we can differentiate an expression, right, a sum or difference of individual terms singly, we can also find antiderivatives by going term by term singly as well, right? So we can just handle this one at a time. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. 5 is a constant with respect to b. That must have come from 5b, because the derivative of 5b with respect to b is just the constant 5. And then lastly, a plus c, right, because we don't know. Raise your hand if you had number 4. All those terms correct? Good job, you guys. Number 5, this is why we use exponentials with base e, because their derivatives are cyclical. So too are their antiderivatives cyclical. They appear, the exponential appears in its derivative and antiderivative, so e to the u plus c. And lastly, 1/2 sine of 2z plus c. Raise your hand if you had number 6, the same in blue. You had that? So how do we get that 1/2? Right? How do we get that 1/2 there? How did you get that 1/2 as you were thinking about that? James and Amanda?
Because the 1/2 has to cancel out the 2 because you take the derivative of 2z, which is 2. So that equals 1.
Absolutely. If you were to differentiate this original y, right, in accordance with the chain rule, we've got a constant multiplier out front, the 1/2. Sine differentiates to cosine with the angle of 2z, but then times the derivative of the inner function. Times the derivative of the angle would spit out a 2. Since there was no 2 there in my derivative, right, I must account for that by canceling out with a 1/2. Now my 1/2 times the 2 derivative of the inner function gives me the 1 cosine 2z, which I had original. So that's going to be pivotal in our discussion today as we look at more complicated examples. Nice job, you guys. And so this process is known as anti-differentiation. So anti-differentiation is what this process is, and that's what you can include for your last one, which isn't up here. So anti-differentiation. And that's fun spelling. Whew. Comes up red in your spell checker all the time. Your spell checker is not calculus ready. Okay, so as a result of our first foray into anti-differentiation with partners, we've got one of our antiderivative rules. And just like we had derivative rules, we'll need antiderivative rules. Guys, we have an anti-differentiation rule for the power rule. The derivative of a power function is exponent times the base and then raised to 1 less. So if we're going to go backwards and reverse that process, the first thing we'd have to do is add 1 to the exponent. So this would become x to the n plus 1, and then divide by the new exponent. So divide by the new exponent. So once again, an antiderivative for x to the n with respect to x is x to the n plus 1 divided by n plus 1. That is, add 1 to the exponent and divide by the new exponent. So for our simple power function x to the n, we will add 1 to the exponent and then divide by the new exponent. We'll add 1 to the exponent and divide by the new exponent. This power rule holds true, right, for all powers n except if my current power is -1. Notice how this falls short of an anti-differentiation rule, right? If we were to add 1 to this current exponent, -1, we would get 0, right? So if this current exponent in the second rule is -1, -1 plus 1 would be 0, x to the 0, we can do that. But then dividing by the new exponent would be dividing by 0. And so we cannot apply the power rule for antiderivatives if my original function has x to the -1. Instead, what you recognize is an antiderivative for 1 over x. Just from your derivative rules. What must that have come from? Danny?
Natural log?
Yeah, the natural log. Okay, so this must have been a natural log function. All right, now, we're going to account on this later, so for now, we'll include absolute value bars around my independent variable, ln of absolute value of x, to account for my domain restrictions. I know this hyperbola exists in both the left and right of the y-axis. However, ln of x only exists to the right. So to counteract that, we'll go ahead and include bars, and now we can exist to the left and to the right of the y-axis. But we can't neglect to include a plus c, and so make sure that you include plus c here and plus c. All right, we're not going to be dealing with the natural log today. I just want to include it because that's where the power rule falls short. We're going to be working with the top one a lot, as well as our trig rules today. Let's go ahead and get started. We're going to look at an informal way for finding antiderivatives like you did with your partner, and then a formal way for finding antiderivatives known as u-substitution. U-substitution provides a systematic way for algebraically generating that constant, that 1/2 in number 6, to figure out where that came from, and it utilizes differentials, the concept investigated last time and introduced in Activity 5.2. So we're going to do this 2 different ways. Thanks for bearing with me as we go and do this 2 different ways. Some of you are going to like to complete these informally for the Unit 5 test, and that will be fine. Some of you are going to like to use u-substitution, right? And that will be fine as well. So there's going to be a split within the class, and that's okay. Different learning styles and different preferences are going to exist in any classroom, and so it's okay if you want to use u-substitution. We will need u-substitution for 2 things on the AP exam, and we'll talk about that second semester. But for now, we'll use it as a means for algebraically determining that missing constant. All right, so right now, the integral of sine of 4x looks a lot like number 6 on your differential equations review that you completed with your partner. In fact, I don't have a rule for sine of 4 of x, but I do have a rule for sine of x. If it just had been sine of x, I would know where that came from. So what we're going to do is we're going to choose u, right, as a means for rewriting the original integral as a function that I do have an antiderivative rule for. So we're going to let u be 4 4 of x when we perform u substitution. Then I'd be working towards integrating, that is finding an antiderivative. If I were to substitute that u in for the 4x, I'd be looking towards integrating sine of u. And I have an antiderivative for that, right? That must have come from a cosine, opposite cosine function, right? Because then opposite of cosine would differentiate to positive sine. So in this technique called u substitution, we choose u so that when substituted into the original integrand function, that's sine of 4x, we're left with the rule that we know. We know an antiderivative for sine of u, it's negative cosine of u. However, my original integral was with respect to x and had this dx differential here, telling me that my independent variable in my antiderivative function is going to be x. Here, my antiderivative function is going to include u's in it. And so I need, in order to do this, I need to have a du here so I can tell exactly how my dx and du relate and can go backwards and find an antiderivative. So enter our differential. We're going to differentiate this u with respect to x. If u is given by 4x, then we'll take the derivative of both sides. That is, the derivative of u with respect to x must be what? Well, what's the derivative of 4x with respect to x? 4. And I want to see what I have to plug in for this dx here. I've already got the sine of 4x taken care of. That's sine of u. But I still need to see what I'm going to put in for that dx. And so what I'll do is I'll multiply that dx over and then divide by the 4 to solve for it, and I'll see exactly what to plug in for dx.
Sounds incredibly exciting. Brady Anders.
All right, so we're going to go ahead and see what we have to put in for that dx. We're going to do that by multiplying my dx over to the other side. So du equals 4dx. And then dividing over the 4, so it looks like 1/4 du is what's equivalent to the squiggle underlined dx. Now this might seem like a long, involved process, right, for seeing that I needed a constant of 1/4. And that's okay, right, because they're going to get more complicated, and I want to use this as a means, as a foundation, so you can see how to algebraically get the constant if you need to. So let's complete the substitution. Sine of 4x went to sine of u, but we still need to put in for dx. What is dx equivalent to? 1/4 du. So I'll put 1/4 du in for dx. And now I have an I have an integrand function with u's in it. I have a differential saying I'm going to have u's in my antiderivative. I'm ready to go. I'll grab onto this 1/4 constant multiplier and put it out front. I'll find an antiderivative for sine of u. What's an antiderivative for sine of u? Well, opposite cosine of u, right? What would be opposite cosine of u? And then because we're doing an indefinite integral without limits there, we're going to have to include a plus c. And since my original function had x's in it, I'll have to resubstitute in my u value, which is 4x, in order to get my final answer with x's in it. So negative 1/4 cosine of 4x plus c. And we found an antiderivative. How could I verify that this antiderivative function is correct? Well, we can always, always, always differentiate. That is, go backwards and see if we generate the original integrand function. Let's go ahead and try that. So the derivative of negative 1/4 times cosine of 4x will be a constant multiplier, negative 1/4, times the derivative of cosine of 4x. Well, cosine would differentiate to opposite of sine. So opposite of sine with the angle. My angle was 4x. And then times the derivative of the angle. So what's the derivative of the angle? 4. If I look at simplifying this, I get negative times negative, that is a positive. 1/4 times 4 is 1, and I get sine of 4x, my original integrand. And so we've checked our answer by differentiating, and we see that we have in fact found an antiderivative. We've got that box in blue, right? Awesome. Now, that takes a while. So u substitution certainly is not necessary if you can if you can informally determine what that constant is. So you don't have to do u substitution, but it's going to be useful when they get more complicated. So as I look at this one, this is the same exact problem. If I were to do this informally, I'm thinking in my head, okay, so this must be a trig function because I know the derivative of a trig function is a trig function. So I know this must have come from a cosine function, a negative cosine function. And my trig rules say the derivative of a trig function is the derivative of the trig function with the angle, right? So I know that if my integrand function had a 4x in it, then my original must have had a 4x in it. And then times the derivative of the angle. Well, what's the derivative of 4x? 4. And did I have a 4 multiplier there? No. So what must I do? I must account for its absence by including a 1/4, just like Grace did with number 6, right? She included a 1/2 to account for the derivative of the angle, which was 2. 2 times 1/2 gets me back to the 1 integrand. Here, 4 times 1/4 would get me back to the 1 times sine of 4x. And so we can't neglect the plus c, but we see how informally we could have generated that much more quickly. So it's fine if you recognize this informally, but you have to be very good with your derivative words in order to do this informally. Let's go ahead and take a look at another. Do I have an antiderivative rule for e to the 2x? No, but I know the antiderivative of e to the u is e to the u plus c. Danny wrote that in our differential equations review that came up to the board. And so if I could choose u to be that 2x, right, then I'd be working towards integrating e to the u. And I have an antiderivative rule for that. Isn't the antiderivative of e to the u? Right, plus c? Good. So let's let u be 2x. Then du dx would be the derivative of u with respect to x would just be 2, multiplying the dx over, so that I can get an expression for that relates du and dx would give me 2 dx. So it looks like 1/2 du is equivalent to this dx in my original. So I know what to substitute in for it. And this is a means to algebraically generate that constant, right? So that I know what that constant is. So let's go ahead and substitute in. My e to the 2x becomes e to the u. My dx becomes what? 1/2 du, right? It's equivalent to 1/2 du. And now we're ready to, I'm going to put that in blue, I think. And now we're ready to anti-differentiate. I know I'm integrating a function with u's in it with respect to u, so I'll have u's in my antiderivative. The antiderivative, move that 1/2 in front, and the antiderivative of e to the u is e to the u plus c. However, because my original function had x's in it, we'll do one more substitution back in. We'll rewrite that u as 2x, and I'll have my final answer. So 1/2 e to the 2x plus c. There you go. Watch where that lands. I might need it later. So was that overkill? Well, in a sense, yes, right? We could have reasoned out what constant we needed informally, right? We could have reasoned out what constant we needed informally by using our derivative words for exponential functions. And so I'm thinking, because I'm good with my words, informally, I know that an exponential function differentiates to itself. So a parent function, an antiderivative function, are you my mommy, for e to the 2x must have been e to the 2x, the exponential itself. However, if I were to differentiate this exponential function, e to the 2x, I would generate e to the 2x, the exponential itself, times the natural log of the base. Well, ln of e is just 1, so that won't change anything. But times the derivative of the exponent, right? Times the derivative of the exponent. What's the derivative of this exponent? 2. And was there a 2 here? No, so I must account for that fact by including what? Well, 1/2. So I can informally generate that constant as well, so long as I'm very good with my derivative rules. Don't neglect to include the plus c, and a quick check to make sure we're correct. The derivative of 1/2 e to the 2x plus c would be constant multiplier times the derivative of e to the x is the exponential function itself, times the derivative of the exponent, times the natural log of the base. The natural log of the base e is just 1. 2 times 1/2 is e to the 2x, and that's my original. Okay, so you can do these informally so long as you're good with your derivative. What questions do you have on the first two? All right, let's go ahead and take a look at another then. I want you to quietly tell your partner what you would choose u to be. So based on this expression for my integrand, what would you choose u to be so that we did have a rule? Right, what would you choose u to be? What would you choose u to be? What would you guys choose u to be, Alex and Riley?
4x.
4x, awesome. So let's choose u to be 4x. Raise your hand if you pick the same thing for u. Good. Then du dx would be given by 4. And multiplying the dx over and dividing by 4 tells me the relationship between the dx and the du. I know now what I'm going to substitute in for the dx. I know that dx is equivalent to 1/4 du. I also know that u is equal to 4x, and so I'm working towards integrating cosecant of u cotangent of u times 1/4 du. And now, because I have, with respect to u, an integrand function with u's in it, my antiderivative will have u's in it. Let's do it. Cosecant cotangent must have come from negative cosecant, right? Negative cosecant of u plus c. And so this must have come from a negative, oh, and let's grab the 1/4. There's our 1/4 cosecant of u plus c. Well, because my original had x's in it, then my answer here must have x's in it as well. So let's plug back in for u, and I get negative 1/4 cosecant of 4x plus c. And we can do a quick check. If I wanted to check and see if this were in fact an antiderivative for my original integrand, we'll go ahead and do constant multiplier negative 1/4 times. The derivative of cosecant is opposite of cosecant cotangent with the angle. My angle was 4x. Then times the derivative of the inner function times the derivative of the angle, that would be 4. Let's check. Negative times negative is positive. 1/4 times 4 is 1, and I'm left with cosecant 4x cotangent 4x, which is my original integrand. Okay, informally, can we do the same thing? Absolutely. I know that if I had, right, a cosecant cotangent, that must have come from a negative cosecant original function. And I know my trig derivative words very well. I know that a trig function differentiates to the derivative of the trig function with the angle, so it must be the same angle. And then times the derivative of the angle. What's the derivative of this angle? 4. Did I have a 4 in my original? No. So I must account for that, its absence, by including a constant multiplier of 1/4. Then if I were to differentiate this antiderivative, right, the negative 1/4 times the 4 would be left with the negative 1. Cosecant differentiates to opposite cosecant tangent, and that'll cross out the negative. And then don't include your constant. Don't neglect to include your constant integration. So it looks like informally we generate the same thing. Awesome. Okay. Finally, we've gotten to a situation where it's not just a straight 4x or a 2x, right, substitution. What's different about number 4? Well, in 4, there's not just, right, angle or an inner function here. There is an inner function and an overall function, but they're both algebraic expressions, right? They're both algebraic expressions. When earlier we had a trig function with an algebraic angle, here we've got two different algebraic pieces, don't we? We've got an x piece, we've got an x squared minus 9 piece, and we've got a square root piece, right? All of these are algebraic functions. And so when we're dealing with multiple pieces here, u-substitution is a means for undoing the chain rule. We're trying to choose u, right? So that when we differentiate u, we spit out the other part of the original integrand function. That is, there's two distinct pieces here. How are they related? We want to choose u so that when we differentiate u, we're left with the other part of the original integrand function. So which of these pieces is the derivative of the other, or a portion thereof? What? Which of these pieces is a derivative of the other piece, or a portion thereof? Michael? Is the derivative of?
X squared minus 9.
Absolutely. And so Michael has already correctly identified this x squared minus 9 as my u, the base in a power function, right? If we chose u to be the x squared minus 9, then the derivative of u with respect to x, that is du dx, will be given by 2x. And that is this other piece. Part of that other piece is right there, isn't it? Right? And so we're choosing u so that when we differentiate, we spit out the other piece of that integrand function. So I ask myself the question, in my original integrand, there's two distinct pieces. Which part is the derivative of the other piece or a portion thereof? And it looks to me like x is acting as a portion of the derivative of x squared minus 9. If we were to choose u to be x squared minus 9, we'd be working towards an antiderivative for root u. And I can do that with the power rule. That's just u to the 1/2. Currently, I'd add 1 to the exponent and divide by the new exponent. All right. Is it exactly x dx though? No, it's not. And so let's multiply this dx over to see how I'm going to plug in du's to match my dx's. It looks like du is given by 2x dx. And my original underlined integrand had x dx, and so I need to solve for x dx to see what I'm going to plug in. So I'm going to divide over 2 and get 1/2 du is the equivalent of x dx, what I had in my original integrand. So my squiggle underline goes to root u. My single underline x dx goes to 1/2 du. And now I'm ready to integrate. So what rule will I use when integrating root u? What rule will I use when integrating root u? Sine, cosine, cosecant, negative cosecant, opposite cosecant, cotangent? No, this is overall a power rule. So we'll go ahead and add 1 to the exponent and divide by the new exponent. But first, I'll kick out that constant multiplier of 1/2 so I don't trip on it. Current exponent is 1/2. So I'm going to go ahead and do u to the add 1 to my exponent. So 1/2 plus 1 is u to the 3/2. And then divide by the new exponent. Keep in mind that dividing by 3/2 is the same as multiplying by 2/3. And then we still need a plus c. What just happened here? We treated my original root u as a power function, u to the 1/2. U to the 1/2 is a power function. I'm going to get its antiderivative by adding 1 to the current exponent. 1/2 plus 1 is 3/2, and then dividing by the new exponent in accordance with my power rule. Add 1 to the exponent, divide by the new exponent. So 1/2 plus 1 is 3/2. Dividing by the new exponent is dividing by 3/2. That's the same as multiplying by 2/3 and then my plus c. And then we need to rewrite with x's, comma baby. And so 1/2 times 2/3 is 1/3 u to the 3/2 plus c. But we don't want u, we want we want x squared minus 9. To the 3/2. I don't believe it. How could that original function, x root x squared minus 9, right, come from 1/3 x squared minus 9 to the 3/2 plus c? Well, we could check and see if we're right by differentiating that. So let's go ahead and differentiate our antiderivative, our potential antiderivative, and see how we did. So let's grab the constant multiplier. That 1/3 will stick around as a multiplier. And now let's do the power rule. The derivative of a power function is the exponent times the base raised to the 1 less. What's 1 less than 3/2? 1/2. And then times the derivative of the base. My base in the power function was x squared minus 9. What's the derivative of the base? 2x. Oh gosh, that doesn't look anything like our original. Or does it? 3, 2 times 1/2. X squared minus 9 to the 1/2, and then there's my x. There's my lonesome x out in the front. You see it? And so we can systematically generate, right, the constants that we need in a process known as u-substitution. Informally, we could do this as well, but it's a little bit trickier. So while the first ones were easy to do informally, right, now they're building in complexity and it's getting a little bit trickier. So if I treat this as two different parts, I recognize the x is acting as part of the derivative of the inner function. In accordance with the chain rule, the derivative of the power function is exponent times the base raised to 1 less times the derivative of the base. And so I know that this x is acting as part of the derivative of the base. I'm going to squiggle underline that base and then ask, what's the derivative of that base in my power function, x squared minus 9? Well, the derivative of that base would be 2x. And so I have that 2x right there, right? Wait, I didn't have the 2, though. I just had the x. So what do I need to do? I can account for that by canceling out with the 1/2. So I've written in my 2 to show that the derivative of x squared minus 9 is 2x. But I can't just add a 2 there because I feel like it or because I need it unless I then go and cancel it out with the 1/2. So I haven't changed the value of my original integrand at all. Right? 2 times 1/2 is still 1 like the original. And so I know this must have come from a 1/2. Add 1 to the power. This becomes x squared minus 9 to the 1/2 plus 1 is 3/2. And then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And I need a plus c. And then hopefully this will work out to the same as last time. We have a 2. And we have nothing else to cancel. So it looks like a 1/3 x squared minus 9 to the 3/2 plus c. How do we do? Oh, snap. There's our 1/3 x squared minus 9 quantity to the 3/2. All right, let's try another. On your own, go ahead and choose u. All right, go ahead and choose u. I mean, on your own with your partner. I mean, on your own without me. But with your partner, go ahead and let's perform this integration. Let's see if we can determine the correct constant, my final answer. So go ahead and try this one with your partner and be ready to share with the whole class. Think about what will be the overall or outer function versus the inner function.
What happens to oh, so that's just treat it as oh, reducing to you. Yes, yes, right.
Awesome, you guys are doing very well. Please continue working. I'm going to jump in to make sure we can get to our later antiderivatives here. Okay, ladies and gentlemen, I'm sorry to interrupt you. I just want to jump in here and I want to see who chose u to be the inner function 3x plus 7. So you chose u to be the inner function 3x plus 7. Excellent. And then we would result in a substitution of u squared, which I know an antiderivative for. I know that u squared would anti-differentiate to u cubed over 3. Add 1 to the exponent, divide by the new exponent. The thing is that my inner function, 3x plus 7, right, differentiates to 3. And I didn't have a 3 multiplier out there. So my du dx equals 3, which means that I'm multiplying the dx over so that I can relate du and dx and complete my substitution. I get du is 3 dx, or a third du equals the dx. Now I know what I'm going to plug in for the dx. I've already substituted in for the 3x plus 7, so I'm going to find an antiderivative for u squared times 1/3 du. So I avoid tripping over it. I'll pull this constant 1/3 in front. I'll now perform an anti-differentiation using the power rule. So I take u to the second, I add 1 to the exponent, that becomes u to the third, and then divide by the new exponent. So that's divided by 3, and then plus c, which means my final answer looks like it's going to be, what, 1/9? 1/9. U cubed, but it's not u, it's really 3x plus 7 cubed, and then plus c. Go ahead and raise your hand if you have 1/9 quantity 3x plus 7 cubed. 1/9? Several of you got 1/9, many of you didn't. No, that's bad news. What happened? Did you get 1/3? Okay, so what do we need? Well, we need a 1/3 from the derivative of the inner function, but we also need a 1/3 coming from dividing by the new exponent 3. So we've got a 1/3 and then a divided by 3 for a total of 1/9. And so we need to make sure we account for, that is, the derivative of the inner function 3. That 3 would be canceled by a 1/3 if you're doing it informally. Then when we divide by my new exponent 3, I get 1/3 times 1/3 is 1/9. Do you see? We have to get a third 2 different times. But for different reasons. One is from the derivative of the inner function, right, not being present, and one is from the power rule. Going backwards, I add 1 to the exponent and divide by the next one. Should we do that informally? Well, we could consider this as, I'm going to scooch over a little bit of space here. And I'm going to go ahead and suppose my inner function is 3x plus 7. The derivative of 3x plus 7, I'll go ahead and say is 3 dx. How about using our differentials? And then I know there was not a 3 there, so what do I need? Well, I need a 1/3. So this 1/3 is going to stick around. The derivative of the inner function is the 3 dx, and I'll go ahead and integrate by adding 1 to my exponent. 2 goes to 3, and dividing by the new exponent. Plus c, so divide by that new exponent 3, and then I get 1/3 times 1/3 is 1/9 times quantity 3x plus 7 cubed plus c informally, and that is exactly what we got. 1/9 3x plus 7 cubed plus c. Oh gosh. Okay, so how are you guys doing? Let's see. All right. You can do this formally or informally. Let's try another one. I'm going to give you guys about a 30-second head start, so you can choose u-substitution or you can provide the constant informally. Some people like u-substitution because it's a systematic method to algebraically determine the constant. Some of you are going to like doing it informally if you're very good with your derivative words. But I'm concerned about you guys missing the 1/9.
Why don't you guys do it informally? After differential.
Oh, it's the multiply. Okay. I think.
What's the D? No, that's the just these are not
Because otherwise you're going to do the product. Well, that doesn't help you at all either. I don't know, what if you use sine and over?
I'm choosing u to be pi x. Raise your hand if you chose u to be pi x. You choose it to be the angle, good, the inner function. We're letting u be the inner function. And that allows us to systematically determine how du and dx relate so that I can get that constant that I need, right? The constant that I need. It looks like I need a 1 over pi du to substitute in for that dx. The u went in for the pi over x, and now I'm ready to integrate. I'm going to integrate my integrand function with u's in it with respect to u, so my antiderivative function will have u's in it. Let's see what we get. Oh gosh, this means I have to know my trig rules. So tangent differentiates to cosecant squared. Therefore, cotangent differentiates to opposite cosecant squared. And did I have the negative? No. So I must have, this must come from a negative 1 over pi cotangent of u plus c. How's that look? Yeah, cotangent would differentiate to opposite cosecant squared. But my original function had x's in it, not u. So final resubstitution, if you will, is going to get an antiderivative function. Looks like cotangent of pi x plus c. I don't believe it. I don't buy that for $1. Well, let's differentiate. Ready? Constant multiplier, negative 1 over pi times the derivative of cotangent is opposite of cosecant squared with the angle. My angle is pi x times the derivative of the angle. The derivative of pi x is pi. Does that work? Negative times negative is positive. 1 over pi times pi is 1. Cosecant squared pi x was my original integrand. Raise your hand if you already had the boxed red. Who already had that? Did you get the pi 1 over pi? The negative 1 over pi, that's much better than the 1/9. That's good news. We're closer, informally. And let's go ahead and take a look at 7. So scooch to number 7 now. I want to make sure that we have time to finish up our discussion. So 2 distinct pieces here, right? 2 distinct pieces. Both the trig functions. So the key here is deciding which portion is the derivative of the other piece, right? And so which of these 2 parts is a derivative of the other piece or a portion thereof? What? Is that a trick question? Because isn't sine the derivative of cosine, and the derivative of cosine is sine? I mean, with negatives, but still cyclical, right? So can we do this? Right? Is one part the derivative of the other part or a portion thereof? How do we want to view this? What do you guys think? Danny? The sine of m is there to act as the derivative of the cosine, right? To act as the derivative of the cosine, so long as the overall function is what kind of function? Is the overall function here a trig function? No way, Jose. Right, Riley, how come no?
Because there's a power there, the 3 and the exponent, so it's a power function.
Absolutely. The overall function here is a power roll. The overall function is a cubing function. This is going to be a power function antiderivative. It's just the base of my power function is a trig function, a cosine function, and the derivative of that base is that sine. And so we need to think of this as an overall power function. In fact, it might be useful to rewrite this as the integral of cosine of n cubed times sine of n dn. Why would it be useful to rewrite like this? Because now you can see the overall is a power function in red. The base of the power function is cosine of m, and the derivative of the base is, or a portion thereof, is the sine of m. Does everybody see that? When we rewrite like this, we can see now we're working towards the overall power rule, where I add 1 to the exponent and divide by the new exponent. To figure out what constants may or may not be needed, right? It might be useful to use u-substitution. However, we can also recognize that this comes from, right, cosine would have differentiated to what? Negative sine. And did we have negative sine? No. And so if we had a negative sign there, then we would be able to do this. We'd simply rewrite this as cosine of m to the 4th power divided by 4. But we didn't have that negative, so what do we need to do? Include it. Let's go ahead and include it. There's my negative. Add 1 to the exponent. Add 1 to the exponent. And divide by the new exponent. And we'll probably see that written as negative 1/4 cosine 4th m plus c. What? I don't believe it, right? How could this be an antiderivative for my original integrand? Well, let's go ahead and check. Can I do it backwards? Probably not. Be safe, Alex. I'm going to come over here. So ready? The derivative of a constant times the function is the derivative as the constant times the derivative of the function. Cosine of m to the fourth is a power rule. Exponent times the base raised to the one less times the derivative of the base. What's the derivative of cosine of m? Opposite sine of m. Let's go ahead and check. Negative times negative is positive. 1/4 times 4 is 1. And I get, by golly, cosine cubed m sine of m. So I've generated an antiderivative, and I've done it using my knowledge of the power rule. So you have to be good with your derivative rules in order to get antiderivatives. All right, we are 2 to go, 3 to go, 8, 9, 10, and then 11 is, well, let's just say stretchers. So we can do this. Do we have an antiderivative rule for 3 to the x? We almost do, right? Don't we? We know that this is overall what kind of function? Power or exponential? Exponential, and I know my derivative words for an exponential function, right? The derivative of an exponential function is the exponential function itself. So I'm thinking this must have come from an exponential function the same kind, 3 to the x, but then times the derivative of the exponent, right? Times the derivative of the exponent. Well, the derivative of this exponent is 1, so that doesn't cause any problems, right? But what piece am I missing here? Yeah, times the natural log of the base. And so if I were to differentiate this, I would get 3 to the x times ln 3. Did I have an ln 3 there? No. And so when I go backwards in my exponential, right, antiderivative rule, I'd have to not times by the natural log of the base, but divide by the natural log of the base. And so that's why an antiderivative for 3 to the x is 3 to the x over ln 3, as opposed to timesing by the natural log of the base when I differentiate, and then don't neglect to include this too. And you can check that by differentiating. See, that wasn't so bad. Now we're just 2 to go. Plus 1. Okay, go ahead and do 9 with your partner. Fast, fast, fast. You don't have to do u-substitution. You can algebraic. You can do it informally if you like. And what did you get for number 9, Colin?
Input e to the 5t.
Raise your hand if you had 1/5 e to the 5t plus c. All right, get that? Informally generate the constant we needed to provide for the derivative of the exponent, which is 5. It wasn't there, so we needed 1/5. Nice job, you guys. Number 10. 1 to go, plus 1. So, gosh darn it. Which piece is the derivative of the other piece or a portion thereof? And so what's the relationship between these algebraic functions? So Danny told us last time, right, which piece could act as the derivative of the other piece. Go ahead and decide which part is the derivative of the other part or a portion thereof. So how are these connected, and what overall rule would be using here? All right, go ahead and share with the class which part is the derivative of the other or a portion thereof. So what do you guys think? Riley and Grace?
T to the third plus 5 would derive to 3t squared. T squared would be part of it.
Absolutely. That t squared is there to act as part of the derivative of the base in this overall power function. Absolutely. Good job. And so if we let u be the t cubed plus 5, right? Then I know when I differentiate and get du dt, I would get 3t squared. And I have that t squared right there. So my du equals 3t squared dt, which means the relationship between t squared dt would be 1/3 du. So what am I going to plug in for underlined black t squared dt? I'm going to plug in 1/3 du, right? That's what I'm going to plug in for the underlined t squared dt. I'm going to plug in 1/3 du. What am I going to plug in for the squiggle underlying green? I'm going to plug in u, so I'm getting u to the 7th. So isn't this just a power rule? I'm going to integrate u to the 7th. So I'll grab my constant 1/3 and I'll put it out front. I'll integrate u to the 7th and get u to the 8/8, bless you, plus c. So I get 1, are you kidding me? 24th quantity t cubed plus 5 to the 8th plus c. I don't believe it. So let's go ahead and try. When I differentiate this, I get constant multiplier times exponent times the base raised to 1 less times the derivative of the base. The derivative of the base, t cubed plus 5 in green, is 3t squared. Let's check. 8 times 3 is 24. 24 over 24 is 1. T squared times quantity t cubed plus 5 to the 7th is my original integrand. Math works. We win. Math works. That's good news, right? Otherwise the world would crumble in the entropic chaos. But math works. So we could also do that informally if you're brave. As I consider this final function, I want you to note that sometimes we don't have a means for finding a symbolic antiderivative, such is the case with number 11. What part is the derivative of what? Well, clearly this is a chain rule because it's not just cosine of x, it's cosine of x squared itself, an inner function, yes? And yet we're unable to algebraically find an antiderivative symbolically because we don't have part of the derivative of the inner function. What's the derivative of my inner function, x squared? 2x, and they don't have an x. Well, we can provide constants and cancel them out or use u-substitution to see how the constant relates. We can't provide an x. We can't put an x there because we want an x there, we need an x there. So we're not able to do this symbolically. So we cannot algebraically evaluate this right now. So while it's easy, right? It's easy to find derivatives. Pretty much we can find a derivative of anything. We can't always find an antiderivative of something symbolic exactly by hand. So we can't do this symbolically. One day. Not in this class, but one day. All right, guys, let's go ahead and fill this in. We've got our 2.5 minutes. It's going to work out perfectly. So please write down. And you can talk quietly with your partner. Just keep it amongst your partner pairs. Indefinite integrals are blanks. When you're evaluating an indefinite integral, one must always include blank, exclamation, exclamation, exclamation. And then considering that integrand, which part is the derivative over the other, or a portion thereof, and what's the overall rule. Please be ready to share on the whiteboard. Okay. Indefinite integrals are blanks. Emily?
Antiderivatives.
Antiderivatives. Indefinite integrals are antiderivatives. Awesome. When integrating, always make sure you include a Andrew. Plus C. Excellent. And lastly, the most important questions, which part is the derivative of the other in the above integrand? And so if we were going to determine which part is the derivative of the other, how would you say these relate? Right? How would these relate? Blake and Vivian?
Cosine of the derivative.
Yes. Cosine of x is a portion of the derivative of the base 5 plus sine of x. if our overall function rule here is what kind of function. So the overall function here would be what? Riley E? Absolutely. So my overall would be a power like u to the 5th. Awesome work, you guys. Good job. We've got OTL number 5 for next time. I'll go ahead and stop and save the recording.